Welcome back. In the last lecture, we have discussed about the Fourier series of 2 pi periodic function. So, now we would like to write the Fourier series in a compact form using the formula e to the power I n x is equal to cos n x plus I sin n x. This is we are quite familiar from our high school days. And so, now the Fourier series, let me write down 0 to infinity, then this is a n cos n x plus n equal to 1 to infinity b n sin n x. This is the Fourier series of a function f, and this we can rewrite it as this 1 by 2 summation over n equal to 0 to infinity a n e to the power I n x plus e to the power minus of I n x, and then this one is 1 by 2 I summation n equal to 1 to infinity b n e to the power I n x minus e to the power minus of I n x. Okay. So, now what we can do is that we can write this as n equal to 0 to infinity a n e to the power I n x, and here if I am taking this quantity b n, then this is e to the power minus of I n x is coming into being. So, this I can write in the form n equal to minus infinity to infinity alpha n e to the power I n x, where alpha n is equal to a 0 if n is equal to 0, and a n by 2 plus b n by 2 I if n is greater than 0, and a of minus of n by 2 minus b of minus of n by 2 I if n is less than 0. That is what is our alpha n in a compact form. So, now this if I am writing it as alpha n from here is equal to, for n greater than 0, 1 by 2 pi 0 to 2 pi f of x, and then this is cos n x minus I sin n x dx, which is equal to 1 by 2 pi 0 to 2 pi f of x e to the power minus of I n x dx for n greater than 0. If n is less than 0, then alpha n, this is again 1 by 2 pi, 2 factor is coming from here, and then 0 to 2 pi f of x, then this is cos of minus of n x minus I sin minus of n x, then this is dx. Now, this is equal to again 1 by 2 pi integral 0 to 2 pi f of x e to the power minus of I n x dx. So, this we can write down as f hat of n is equal to 1 by 2 pi 0 to 2 pi f of x e to the power minus of I n x dx. Therefore, the Fourier series of f is can be written here, n is equal to minus infinity to infinity f hat of n e to the power I n x. So, that is what alpha n, I have replaced it by f hat of n. So, this is the form of the Fourier series we will be discussing throughout this course. Okay. So, now let us compute some of the important functions Fourier coefficients as well as the Fourier series. Remember that we always say that this is the Fourier series of f. We are not claiming that this series converges to f. We are not writing f of x is equal to minus infinity to infinity f hat of n e to the power I n x, because till now we do not have the license to write this statement unless and until we prove that this infinite series converges to f for every point x, then only we can write it down. Okay. To start with, we do not even know for what kind of f this Fourier series is going to converge. To have a feel for that, let us compute some of some functions Fourier coefficients. Okay. So, let us take, let a b is an interval in minus pi to pi. So, here is our minus pi to pi and a b is somewhere here. This is our interval. Now, I take f of x is equal to 1, indicator function of a b. So, we will be using this symbol quite often. Let me write it down for you, the definition, which is equal to 1 if x belongs to a b and which is going to be 0 otherwise. So, now this function is going to be 1 here, constant function 1 here, and then on this it is 0. That is what the function is. Now, it is pretty easy to compute the Fourier series. So, now f hat of 0, this is equal to 1 by 2 pi, only surviving part the length of the interval, this is b minus a. Now, for n not equal to 0, f hat of n by definition, this is 1 by 2 pi, then now this is minus pi to pi, but f only survives in the interval a to b and rest it is outside a b, it is 0. Therefore, this integral now is this e to the power minus of I n x dx, and that is a pretty easy integral to compute. So, this is 1 by 2 pi e to the power minus of I n x by minus of I n, this is a to b. So, this is equal to 1 by 2 pi I n, and then this is a negative sign is over there. So, this is e to the power minus of I n a minus e to the power minus of I n b. That is what is going to be the Fourier coefficient. Therefore, the Fourier series is equal to b minus a by 2 pi plus summation n over z not equal to 0 and 1 by 2 pi I n e to the power minus of I n a minus e to the power minus of I n b. Now, just check that if in particular if if our interval minus a to a for some a which is positive and less than pi, then this one is going to give us, then the Fourier f hat of n essentially is going to be f hat of n, this is equal to 1 by 2 pi of I n, and then this is a is minus of a here and b is a there here. So, therefore, this is going to be 2 I sin n a. So, this is equal to 1 by pi sin n a by n. So, that is going to be the Fourier coefficient of and now, as you can here I had forgotten this e to the power I n x has to be there. Yes, that is the Fourier series, this is only the Fourier coefficient. And similarly, if we want to get another example, that f be 2 pi periodic and f of x is equal to mod x if on minus pi to pi. So, this is nothing but the graph is something like this. So, this certainly is an even function, therefore, f hat of 0, this is equal to pi by 2, because this is nothing but the integral of 0 to pi x dx. And f hat of n, this is equal to 1 by pi 0 to pi, then this is an even function. So, I can write it in terms of the cos n x dx, which is equal to 1 by pi. We have computed this, and then this will get the twice the derivative. Okay, let us compute it for this. So, this is sin n x by n 0 to pi, that is going to vanish the first part, and then minus of 1 over pi, and then this is 0 to pi, this is sin n x by n dx, this is equal to, this is 0, this is minus 1 by pi, sin integral is negative. So, this is minus pi n, this is cos n x by n, then this is 0 to pi, then this is 1 by pi n, and then this is minus 1 to the power n minus 1, and then this n is n square. There we go. So, now if this is equal to, if n is even, then this is equal to 0, if n even. If n is odd, then this is minus 2. So, minus 2 by pi n square, if n is odd. So, therefore, the Fourier series is equal to pi by 2, then plus 2 by pi and summation over n odd, and so now this is remember that this is minus infinity to infinity. So, positive term if I am taking, then and negative term here it is coming out to be n square. So, I can multiply by 2 and I can consider n is greater or equal to 1. So, this is 1 over n square, and then this is cos n x. Now, suppose the Fourier series converges for every x, because here as you can see the Fourier series is nothing but this is bounded by 1 over n square. I know that this series converges. Therefore, the Fourier series converges. Now, we are not sure whether the Fourier series converges to f or not. Let us grant ourselves for some time that the Fourier series, which is a convergent series because of 1 by n square. Now, this converges to f at every point. So, in particular it converges at x equal to 0. So, now if Fourier series converges to f, then at x equal to 0, f of 0 is 0. So, we are going to get 0 is equal to pi by 2. Here there is a minus sign I have missed out. Here there will it is a minus of 2. So, now minus 4 by pi summation over n odd n greater or equal to 1 by n square. Therefore, this will imply that summation n odd n greater or equal to 1 by n square is equal to pi square by 8, if I am taking it to the other side. So far so good. Now, if I am writing summation over n greater or equal to 1 by n square, this I can break it summation over n odd n greater or equal to 1 plus summation over n even and n greater or equal to 1. Now, if the second sum n is even means I can write this as n equal to 2 k, k from 1 to infinity, that is the even part. So, this essentially becomes summation n odd n greater or equal to 1 by n square plus, then this is 1 by 2 k, means then that will be 1 by 4 k square, because if n is equal to 2 k. So, this is 1 by 4 summation over n even n greater or equal to 1 by n square. This implies that 3 by 4 summation n greater or equal to 1 by n square is equal to pi square by 8. This implies that summation over n greater or equal to 1 by n square is equal to pi square by 6, which we know already. So, this as we can see that if we can prove that actually this Fourier series converges to f at every point, then we are getting that summation over 1 over n square is equal to pi square by 6, not bad at all. So, so now let us ask ourselves the question of the convergence. So, there will be some other example and exercises would be given to you in the assignment. So, please do try to do as much as you can. So, now we have seen that the Fourier series is f hat of n e to the power I n x, summation varies from minus infinity to infinity. Now, we are questioning the validity of the infinite series, that means whether the series is converges in the first place or not. So, now let us try to see certain behavior of this Fourier coefficients. Now, already we have seen that if f is odd, then f hat as a function in z, remember that we can now treat f hat is a map from z to c, this is also odd. Simple computation, and if f is even, then f hat of minus of n is equal to f hat of n. That means, f hat is as a function on z is also an even function. Now, for the convergence, then it is the least because we want this to converge. Then first the least we ask for that this has to be bounded. If there is a function f for which the f hat of n is not a bounded function, then there is absolutely no question of the convergence of this series. So, now in order to show that if f hat of n, mod of f hat of n, I can write that this is 1 by 2 pi modulus 0 to 2 pi f of x e to the power minus of I n x dx. Now, by triangle inequality, this is 0 to 2 pi mod f of x dx, because e to the power I n x mod is 1. So, which is f is a Riemann integrable function. So, therefore, this is independent of m, this is equal to let us say m f. Therefore, supremum of n varies over z, mod of f hat of n, this is finite, because this is no more right hand side is no more dependent on f. Okay. So, now let us take f belongs to C 1 0 2 pi and 2 pi periodic. So, remember this C 1 means f is differentiable and f prime is continuous. If you recall, so when we are talking about the continuity and the differentiability of the function f, then we had this definition that f of 0 is equal to f of 2 pi, because this is kind of a periodic function on the circle we are looking at the continuity of f. So, for now f hat of n, if we compute x dx. Now, because we had given with the differentiability condition of f, therefore, we can apply integration by parts. So, now if I apply that, this is f of x e to the power minus of I n x by minus of I n, provided n not equal to 0, and then this is 0 to 2 pi, and then minus plus 1 by 2 pi I n integral 0 to 2 pi, this is f prime of x e to the power minus of I n x dx. Okay. So, now as here because f prime is a continuous function, therefore, this integral exists. That is why we are taking that it is in C 1, that means the f prime is again a continuous function. So, now if we compute this, now this is f of 2 pi, then this is all the 2 pi periodic function, f is a 2 pi periodic function, e to the power I n is a 2 pi periodic function. So, therefore, the first quantity will vanish. So, we have got 1 by 2 pi I n and 0 to 2 pi f prime of x e to the power minus of I n x dx. Now, if I take the modulus of f hat of n, now as you can see this is less or equal to 1 by 2 pi of n integral 0 to 2 pi mod of f prime of x dx. Very interesting. So, we have given certain smoothness on f, we are assuming that f is differentiable and f prime is continuous, then we are getting f hat of n have some decay, because this is mod n of course. So, now if mod of f hat of n is less or equal to some constant which depends on f by mod n. So, at some decay. So, now it is natural to us, suppose if I increase the differentiability of f, that means or in other words the smoothness of f, then let f is in C 2 of 0 to 2 pi. That means f double prime exists and this is in C of 0 to 2 pi. Essentially that will imply that f double prime is going to be integrable. So, again by the repeated integration by parts. So, now f hat of n is 2 pi 0 to 2 pi f of x e to the power minus of I n x dx, which in the first part it will be 2 pi f x e to the power minus of I n x by minus of I n n not equal to 0, and then this other integral would be part will be n I 0 to 2 pi f prime of x e to the power minus of I n x dx. Now, this goes 0 because this is 2 pi periodic function, we are left with this. Again we play the same game, integration by parts. We have f prime of x e to the power minus of I n by minus of I n, then this is 0 to 2 pi, and then plus 1 by I n, and then integral 0 to 2 pi f double prime of x e to the power minus of I n x dx. Now, as you can see this first part is 0. Now, for the second part what we are going to get this I n. So, this is equal to, if I take it, then this is minus 2 pi n square and 0 to 2 pi f double prime of x e to the power minus of I n x dx. Now, if I take the modulus f, then this is less or equal to some constant which is depend on f, that is f double prime, this divided by n square, more decay. So, now what we have observed here? So, if f we are increasing the smoothness of f, we are getting the decay in f hat, more and more decay in f hat, exactly following the same argument. If f is in C k of 0 to 2 pi, then mod of f hat of n is less or equal to some constant C f that will depend, of course, with now you can see that this is integral of mod of f k plus of k, and then this is mod n to the power k. Therefore, we can conclude here that the more smoothness, we are guaranteeing the Fourier series to converge absolutely, because we have for twice differentiable, we have 1 over n square decay. Therefore, the Fourier series is going to converge. For thrice differentiable, we have mod of n q. So, absolutely that is no problem at all. So, more and more smoothness will give more and more decay in the Fourier coefficient. Okay, thank you.